Hi, yes, this is Adam here. I'm recording a short tutorial on Moses with Neil from OpenCog. G'day, Neil. Welcome.
Hi. Yeah.
So this is
So
just very informal. We're talking about Moses
yeah.
here.
We are highly unprepared, and I'm tired and I'm tired and sick. So I'm not. I probably won't be very efficient, but I'll try my best. Um. So um. Like, can you see the screenshot?
Yeah, I can see data
Yeah.
CSV in the top right hand corner
Yeah.
and the man page in the bottom right hand corner, and then the shell output on the left side.
Yeah. So here we have. It's a very simple example to show how to output Moses model directly in atoms format, which is going to be scheme here. And so we just take a simple data set which has four features. The first feature is the output feature, and the three other features are input features. And we're trying to find a classifier that would predict the output given the inputs. So the output here is named O, and the inputs are named F1, F2, and F3. And they could have any name. It's just by default, the first feature is the output feature. So we don't need to specify any further to Moses that. And so given that we can uh, write a command line starting with Moses, the first argument specifies the problem we're trying to solve. Um,
Mm-hmm.
Pre means precision, meaning that we are trying to maximize the precision of the function of the classifier. And this option here, it means that we want to um, uh, keep the recall under, over a certain threshold, because if you don't do that, given how precision and recall are defined, you could very easily just find a very classifier with a very high precision, but it would be almost useless because the recall would be so low. To
Hmm.
explain what is precision and recall, I think there's a very intuitive picture here on the precision and recall Wikipedia article. So the square is my data set. The circle inside is my classifier. When the classifier, so here the definition of the precision is this area, which are the true positives, divided by the area of my entire classifier. What that means is that when the classifier says 1, well, it's the dot is inside the circle. And when it says 0, the dot is outside of the circle. So
So
to give you,
just for the
yeah.
viewer's interest, what is a classifier? What do you mean by that?
Well, so here classifier would be something that would take, say, a vector of booleans, and it would classify whether this vector belongs to a class or not. So for instance, the classifier could be trying to determine if someone is tall based on various features. I don't know, if he eats a lot, this kind of stuff. And the precision is going to measure, well, it's going to measure exactly this, what is pictured here. Like, to give you an example, say for instance, if you're trying to predict, say, financial market data, you're trying to find a classifier that is going to be able to predict whether, given some data, the price is going to go up. So if you find a classifier that is extremely good, that is maybe almost 100% of the time, it's going to be able to find that when it says the price is going to go up, the price is indeed going to go up. But maybe this classifier will have, so let me rephrase that. So if you have such a classifier, it will have a very high precision. Basically, what that means is that the red area will be almost non-existent. It might be tiny, it might be a tiny circle, but it will be almost always be right. That might be nice, but the thing is that if your classifier is right and gets triggered, I mean, once a year, well, that's not very useful. So you want to pay attention to the recall. So the recall is going to be amongst the positive instances, that is, amongst the instances where the price actually went up, how many times the classifier got triggered. And so basically, yeah, do I need to explain more about precision recall, or?
I think that's okay. Yeah.
I mean, I think you got the idea. So it's okay if it's not completely clear, but the idea is just that the recall is, if you set the threshold of the recall, this is going to force MOSES to try to find a classifier which is going to classify more instances. Otherwise, it will find refuge with the few instances that MOSES is very good at classifying, and forget about the rest. And so these kind of fitness functions are, I mean, they do explicitly create an asymmetry between precision and recall, which some other fitness functions don't. For instance, F1 doesn't. So I don't know if I have to explain what it is, but say, for instance, accuracy, just measuring, like, the accuracy is going to be a fitness function that is going to account for basically the precision of not triggering the model as well. This is more adequate when you're trying to find a model that says something like, this thing belongs to this class or not this class, given that not this class is just as meaningful as this class. And using a precision type fitness function is more adequate when you want a model that will find, when you want a model that is able to predict that something belongs to this class, or else I don't know. Yeah. And what the recall says is that you want to know at least a little bit above a certain amount. Otherwise, it's too easy. Right. So Right. So let me continue with the argument. So we were here. So this is purely to define the fitness function. This is to tell MOSES that you want to output you want to put in the models directly the names of the features. I might show that actually. It's going to be clear. Let me run that. As you can see, well, okay, let me finish first. And I'm just quickly finishing, and then I'll compare the different parameters. So here it's just to say, run this fitness function on this data set.
Okay.
The little one in the this is to use 4 jobs. I mean 4 threads.
Okay.
To be faster. And this specifies the output format. So here it's scheme. Well, it's scheme for the atom space. It's not scheme in general.
Okay, yeah. So you've got various different output formats. One of them is scheme. What are the others?
We have Python, and we have a combo, which is the native language of MOSES. I mean,
right. So people should know that a basic understanding of combo is useful if you want to understand MOSES.
Yeah, sure. It is not. It's not a special language. It's just that it's been tailored for MOSES, but it has nothing special really, and it could have been otherwise. So this option is to, well, tells how many models you're going to show. So here it's 100, but MOSES probably didn't find 100, so it outputs all the ones up to 100 that it found. Okay, so now let's go through the results. So now what we have here is, right, so what this model says is, what this model says is that feature F1 is a very good predictor of the output, and that's true. So it has a precision of 1. It's a perfect predictor. It happens to have a recall of 1 as well, but that's not necessarily what we are after. We have also F3, and then we have other models. So here, top is, this is basically the true predicate. And bottom is the...
So you should say F3 is also a perfect predictor of the output.
Yeah. F3 is also a perfect predictor. Top is the true predicate. So, well, it's top is that. 1 everywhere. Oh, that's going to be. And so it's only right half of the time. Okay, so you've got the precision of 0.5. And then you've got other predictors. So these ones they're okay, but they're more complex. That's why they're coming after. And then, well, you've got other predictors that are worse and worse.
Oh, yes.
Yeah. And so, as you can see, the output is actually a, how am I going to say that? it's a high yeah. Well, I'm not sure there's a better way to say that, but it's a. Sorry, I'm very tired.
Yeah, that's understandable.
But
Is it a high confidence, highly confident predictor?
all right, right. So here's the thing. So this information is not output here. I forgot whether it is output at all, or whether I'm not sure whether I had some scripts to do that.
So.
I'm just not sure. I forgot that. Like if I let me try confidence. No. Count. No. No. No, I don't think it's here. So it's probably in the scripts that you put on the wiki page. Can you hear me?
Yeah, I can.
Yeah. Because it's not here, and well, the confidence is obviously very low because we only have 4 observations, and in fact we have even. I mean, since we're talking about a precision type fitness function, we even have less. We have 2 observations actually, because F1 is triggered only twice, here and here. So 2 observations makes a pretty low confidence. Well, so for instance, if I were to if I were to put 0 here, I would get variable numbers, placeholders, like in Bash, basically. And so, I mean, depending on the context, you might want these, or you might want to link to the feature names. I mean, whatever. Yeah, I think that's about it for MOSES outputting in Atomis format.
Right.
So now there are other tools which I have coded, but I haven't used for a while, which I think are the tools which are on the wiki page.
Yeah. But how about getting now that we've got the atoms out? That's how to. That's an introduction to to MOSES, or how to get some output there. But how do we push that into the atom space?
Yeah. Sorry. Can you repeat that?
Okay. So now, how do we get that output into the atom space and use it?
Yeah. Well, so for instance, you can so you can just load it like you load any scheme file. You can pipe it in the telnet console, which is going to transmit that to the COG server and load it to the atom space. But you need to have proper scheme. That is, you would have the. Oh yes. So yeah, now I remember. Okay. Right. So the scripts that I wrote on top of that were taking these models and creating, depending on the fitness function, although I think only the prediction fitness function was supported, and I'm not sure. But the idea was, depending on the fitness function, you would take the model, you would take the the score, and you would create a a sub hypergraph that would represent basically the semantic of this model being a good predictor of this data set according to some fitness function. I forgot how far I went with that, but that was the idea. And so to give you a concrete example, I think that's where I'm looking at what you've written, expert models and fitness, and I'm pretty sure it's these. Relate features and machines.
Yeah.
Yeah, that's got to be these. So let's have a look at this file.
You can expand.
So a little script to explore. Blah, blah, blah. Yeah, so that was really
Perhaps we should like create another section to talk about how to get it into atomspace. Because I think our viewers might be getting
maybe, but just because now, I mean, we're looking at it at the moment, so I can I can say a word about it. I mean, I still need to think a little bit, but oh, right. Okay. Let's go through that. It's interesting. So the model itself associated with its label. Why do you have a predicate? Oh, yes. Okay. So the model here is going to be what has been output by MOSES. It's going to be one of these guys. Okay. So here it's very simple, but of course in practice it might be a monster. So it's good to give it a name and to refer it by its name. So that's what this thing is doing. I think today we would probably use a define link, but at the time I used the equivalence link, which is semantically equivalent here in this context. The label associated with its accuracy. All right. Yeah. Oh, okay. Well, okay. So to record the so again, why the accuracy? Because maybe you want to use, instead of maximizing the precision, you want to maximize the accuracy. So now this representation using an evaluation link and a predicate node accuracy is basically to not have to bother formalizing accuracy in OpenCog, but this would be easily doable. I'm not sure it's even a necessary shortcut, but anyway, that is what was done at the time. What do we have here? Balance accuracy. Okay, it's similar. So here, because the implication link, the TV on the implication link may directly represent the precision, we can directly use an implication link. So what's going to happen? So I might just build one just to give a bit more, to make this a bit more concrete. So we have the model predicate name, target feature name. So basically, what this script would do is that it would take the models. So let's take this model, for instance, and it would write something like that. Well, it's very useless, but let's do it. Some confidence. I'm not going to define that now. Okay, would essentially have the model, although here in practice it would be its name, but it's equivalent to the model itself. And my output feature, which was O. And that's it. So here we have the knowledge that this model is a very bad model because the strength is 0. So now the other thing is to define the confidence. And I think the confidence was, I'm not sure. I mean, maybe it's got to be somewhere here. But basically, I think it's probably going to be something like number some k, and n would be the number of observations that allowed you to estimate the strength, which is 0 here. And in this example, well, that's 2, because, yeah. Oh, well, I don't know if that's 2. It's not specified here. But it is whenever this model is active, that is, it outputs 1, which is going to be between 0 and 4. And that's it. And so once you have that, well, you can do whatever you want with it. You can use it for reasoning, or yeah. And that was it. That was the idea.
Awesome. Cool. Right. So yeah, there's some examples, some biology examples that that exist somewhere. It might be worth having a look at those. Not now, but in another screencast or something. Yeah.
Sure. Okay. So I didn't really. I mean, I followed very loosely what was happening with the practical use of this. So I might be. I mean, I might not be the right person to comment on that any further, but yeah,
Mike Duncan did the biology stuff.
Yeah,
so
I think Mike
about the data. So yeah, I was going to talk to him too. Yeah. Hope that's been really exciting for our viewers. It's not the usual thing you see on this channel, but hey, you can expect anything in the next few years. Who knows? Okay. Well.
Okay.
Right. Thanks for the tutorial.
Well, you're welcome.